In this video, we're going to look at some more complicated derivatives that involve multiple rules. So first off, let's look at C here. Hy equals cosine of 10y over e to the 4y, plus 1. So we can see a composition in here and here, but the overall structure is a quotient. That means when we go to find the derivative, it's going to be structured via our quotient rule. So h prime of y, and let's write that out in pieces. We'll have our denominator. So e to the 4y plus 1, that plus 1 was not in the exponent. I know it's hard to tell from my writing, times, we're going to do the derivative with respect to y of the numerator. So first thing I'm doing is I'm just setting up my quotient rule. I'm not actually taking the derivatives within my quotient rule just yet. Minus, now I'll hold the numerator constant, cosine of 10y times the derivative with respect to y of the denominator, e to the 4y plus 1, all over the denominator squared. Oops, I didn't mean to go that far. E to the 4y plus 1 squared. So this will not be a pretty derivative, but it's not a terrible derivative. So, okay, that part gets left alone. E to the 4y plus 1. Here is going to be a chain rule. Outside function is cosine, inside function is 10 to the y. The derivative of cosine is negative sine, leave the inside alone, 10y, times the derivative of the inside, so times the 10. So that in parentheses right there is the derivative of cosine of 10y. Now we're going to hold the cosine of 10y constant, and this one will get done piece by piece. So first we encounter the derivative of e to the 4y. This is a chain rule because it's a composition. The outside function is e, the inside function is 4y. Now remember, a derivative of an exponential will always have itself in it. So doing the derivative of the outside, leaving the inside alone, gives us e to the 4y. Now the derivative of the inside, which is the exponent, gives us multiplied by 4 because the derivative of 4y is 4. And then the derivative of 1 is just 0, so that's going to go away. All over e to the 4y plus 1 squared. There's not going to be much simplifying we can do in this. If we wanted to write the negative 10 out front here, we could. If we wanted to write the 4 out front here, we could. But we found the derivative, and it's not going to get a whole lot prettier regardless of what we do. So we'll just go ahead and leave it. Let's go on to the next one. S of z equals 2 to the z squared secant of z. So again, it's all about determining what's your inside and your outside function, or what's the structure of your function, I should say, so you can decide what rule to start with. So in finding s prime of z, what we should notice here is this thing is an exponential. So this is going to follow an exponential rule, and then it's going to be treated with a chain rule because the exponent is more than just z. There's the composition. Outside function is 2 to the z, inside function is z squared secant of z. So when we do the derivative of all exponentials have themselves in it, so it's 2 z squared secant of z times ln of 2, because the base is something other than e. Now times the derivative of the inside function, which in this case is the exponent, z squared secant of z. Now here's where things get a little interesting, because this is a product. It's going to require product rule. So s prime of z is going to be 2 to the z squared secant of z times ln of 2, and now times a product rule. So I'm going to hold the first part constant, z squared, times the derivative of secant, which is secant z tangent z, plus, now I'm going to hold the secant of z constant times the derivative of z squared, which is 2z. Once again, this derivative is not going to get a whole lot prettier, so I'm not going to worry about simplifying. But I wanted you to see how we decide which rule we use first, and that some of the other rules may come out inside of it. So this was a chain rule for the initial structure, within the chain rule, we needed a product rule. Last one, sine of e to the x squared. This one's kind of a cool one, and you're going to see what's going to happen as we start to find c prime of x. First off, we see the composition. E to the x squared is being put in for sine of x. So our first approach is a chain rule. Derivative of the outside, so the derivative of sine is cosine. Leave the inside alone. E to the x squared times the derivative with respect to x of e to the x squared. Now, notice what we have here. We have another composition. So this is going to be a double composition. Cosine of e to the x squared times, now the derivative of e to the x squared is the derivative of the outside, so the derivative of the e function. Leave the inside alone, so it's just itself, e to the x squared. We don't need an ln because the base is already e, times the derivative of the inside, x squared. Well, that's a simple power rule, and that's not a composition, so when we do the derivative of this, we'll be done. X squared times e to the x squared times 2x. And we're done because we know this isn't a composition. So a couple questions that I routinely get asked is, first, how do you decide which rule to use first? You need to look at the overall structure of the function. The second is, how do you know when you're done? Well, when the function you're taking the derivative of no longer requires the chain rule, you know you'll be finished.